Hi dear students, welcome you all to today's class. In today's class, we will be going into a different world in which charges are at rest, that is electrostatics. Yes, today we will be studying the first unit of your plus 2 physics textbook, Electrostatics. Just the lesson will be introduced and the basic properties of charges will be explained and Coulomb's law will be discussed in this video. Basic properties of charges. There are certain basic properties of electric charges. Let us see them one by one. The first property is electric charge. Most objects in the universe are made up of atoms, which in turn are made up of protons, neutrons, and electrons. These particles have mass, that is an inherent property of particles. Similarly, the electric charge is another intrinsic and fundamental property of the particles. The SI unit of charge is Coulomb. The next property is conservation of charges. When one object is rubbed with another object, charges get transferred from one to the other. Before rubbing, both objects are electrically neutral and rubbing simply transfers the charges from one object to other. For example, when a glass rod is rubbed against silk cloth, some negative charges are transferred from glass to silk. As a result, the glass rod is positively charged and silk cloth is negatively charged. From these observations, Benjamin Franklin concluded that charges are neither created nor destroyed, but can be transferred from one object to other. This is called conservation of total charges. So, what is conservation of electric charges or law of conservation of electric charge? Law of conservation of electric charge states that the total electric charge in the universe is constant and charge can neither be created nor be destroyed. In any physical process, the net change in charge will always be zero. Now, the third property is quantization of charges. Experiments shows that the charge on an electron is minus A and the charge on the proton is plus A. Here E denotes the fundamental unit of charge. The charge Q on any object is equal to an integral multiple of this fundamental unit of charge. That is Q equal to NA, where N is an integer having number 0 plus or minus 1 plus or minus 2 etc. to infinity. This is called quantization of electric charge. The charge of an electron is minus 1.6 into 10 power minus 19 coulomb and the charge of the proton is plus 1.6 into 10 power minus 19 coulomb. Now let us go into the important topic of this lesson, Coulomb's law. Consider 2-point charges Q1 and Q2 at rest in vacuum and they are separated by a distance R. According to Coulomb, the force on the point charge Q1 exerted by another point charge Q2 is F12 equal to K into Q1 Q2 by R square R21 vector, where R21 cap is the unit vector directed from charge Q2 to charge Q1 and K is a proportionality constant. Now let us have a glance over the important aspects of Coulomb's law. Coulomb's law states that the electrostatic force is directly proportional to the product of the magnitude of 2-point charges and is inversely proportional to the square of the distance between the 2-point charges. The force on the charge Q2 exerted by the charge Q1 always lies along the line joining the two charges, and R12 cap is the unit vector pointing from charge Q1 to Q2. Then in SI units, K equal to 1 by 4 pi epsilon 0 and its value is 9 into 10 power 9 Newton meter square Coulomb raised to minus 2. Here epsilon 0 is the permittivity of free space or vacuum, and the value of epsilon 0 is equal to 8.85 into 10 power minus 12 Coulomb square Newton per minus 1 meter power minus 2. Now you have to understand one thing. What is permittivity? Permittivity is the ability of a medium to permit flux lines to pass through it. Now the fourth aspect is the magnitude of the electrostatic force between two charges, each of 1 coulomb and separated by a distance of 1 meter, is calculated as F is equal to 9 into 10 power 9 Newton. This is a huge quantity, almost equivalent to the weight of 1 million ton. We never come across 1 coulomb of charge in practice. Most of the electrical phenomena in day-to-day life involve electrical charges of the order of microcoulomb or nanocoulomb. And the fifth aspect is, in SI units, Coulomb's law in vacuum takes the form F21 vector equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square R12 cap. In a medium of permittivity epsilon, the force between 2-point charges is given by F21 equal to 1 by 4 pi epsilon. That epsilon 0 is replaced by epsilon Q1 Q2 by R square R12 cap. Epsilon will always be greater than epsilon 0. Therefore, the force between 2-point charges in a medium other than vacuum is always less than that in vacuum. Now, I already told you permittivity. Now, relative permittivity. Relative permittivity for a given medium is written as epsilon r, and it is the ratio of epsilon by epsilon 0. For vacuum or air, epsilon r equal to 1, and for all the other media, epsilon r is greater than 1. Now, the fifth aspect of Coulomb's law is it has the same structure as Newton's law of gravitation. Both Newton's law and Coulomb's law are inversely proportional to the square of the distance between the particles. The electrostatic force is directly proportional to the product of the magnitude of 2-point charges, and gravitational force is directly proportional to the product of two masses. But there are certain differences. The differences are the gravitational force between two masses is always attractive, but Coulomb force between two charges can be attractive or repulsive depending on the nature of the charges. The value of the gravitational constant is G equal to 6.626 into 10 power minus 11 Newton meter square kilogram raised to minus 2, whereas the value of constant K in Coulomb's law is 9 into 10 power 9 Newton meter square Coulomb raised to minus 2. Since K is much more greater than G, the electrostatic force is always greater in magnitude than gravitational force for smaller size objects. The gravitational force between two masses is independent of the medium. For example, 1 kilogram of two masses are kept in air or inside water. The gravitational force between two masses remains the same. But the electrostatic force between the two charges depends on nature of the medium in which the two charges are kept at rest. The gravitational force between two point masses is the same whether two masses are at rest or in motion. If the charges are in motion, another force called the Lorentz force comes into play in addition to Coulomb's force. And the seventh aspect is the force on the charge Q1 exerted by a point charge Q2 is given by F12 vector equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square into R21 cap. Here R21 is the unit vector from charge Q2 to Q1, but R21 is equal to minus R12. Therefore, F12 equal to minus F21. Therefore, electrostatic force obeys Newton's third law. And the final aspect, that is the eighth aspect, is expression for Coulomb force is true only for point charges, but the point charge is an ideal concept. However, we can apply Coulomb's law for two charged objects whose sizes are very much smaller than the distance between them. In fact, Coulomb discovered his law by considering the charged spheres in the torsion balance as point charges. The distance between the two charged spheres is much greater than the radii of the spheres. With this, I concluded today's class, and we can meet in the next class. Till then, bye.